Okay, hello. I should now be live, hopefully. Awesome. So, sorry for the delay, but we're all good to go now. If you, these are some of the stuff which I've got from the chat. So I will go through them in order. Okay, bit of ASMR early on. Lovely stuff. Right. Equations. Okay. This is the legacy, and this is available on the AQA specification. So if you literally in Google type AQA Trilogy spec, okay, and download it, right down the bottom, it's there. Okay, now obviously in Foundation, you're usually given it. Technically, I think they can, how says it, equations required for higher tier papers only are indicated by that. But in terms of whether you need to remember them or not, I'm not necessarily saying as Foundation you need to remember them off heart, but you need to know how they work. So you might as well remember them. They're not that bad. Okay, I'm going to go through the whole list, and I'm just going to quickly say which paper is which. So this one's a weird one. Weight equals mass times gravitational field strength. That's actually in paper 2 because it's to do with forces. Okay, I'll tell you what we're going to do. We're going to do paper 2 is going to be in red, and paper 1 is going to be in purple. So even though this one is to do with gravity, because it's gravity as a force, it is paper 2. Work done, forces, and it's that's forces. Force applied to spring, fine enough. Forces, that's paper 2. Distance travelled equals speed times time. I think you need to actually know that for maths if I'm right. That is paper 2. Yes, I did. I don't know why I decided to do another live stream. I think I'm just a psychopath. Okay, acceleration, again, to do with forces, paper 2. You'll spot a pattern here. So I don't know why they put the paper 2 topics like at the top of the equation sheet. It's just really annoying. Okay, I'll pretend I didn't see that, Jenna. Resultant force equals mass times acceleration. Again, force equals, that's all to do with forces, so that's paper 2. Momentum, obviously only higher tier, but that is also forces. Okay, now we reach the paper 2 ones. So kinetic energy, that's in the energy unit. Okay, so kinetic energy equals half times mass times speed squared. Okay, or half mv squared. We can think about that in a little bit more detail, but basically v squared means that as your speed increases, your kinetic energy increases exponentially. Okay, so not actually exponentially, it'll be quadratically, but ignore that. It's basically if you double the speed, you quadruple the kinetic energy. GPE, okay, this is a really annoying one. Okay, it'd be MGH. Now, I don't, be pretty harsh of them to, definitely at Foundation, to ask you to rearrange that in any way, shape or form. Okay, but it's mass times gravitational field strength times height. Okay, now these two are basically the same thing. Okay, if you have a look, okay, they've got power equals energy transfer divided by time, and power equals work done divided by time. Okay, now what that means is you only need to remember one of them really, but you can see that actually work done is in energy form, so that's all right. Efficiency, okay, that's useful output over total input, and you can see that these two are basically the same thing. Basically, you can do efficiency in terms of energy, or you can do efficiency in terms of power. So those two are paper 2. So the paper 1, the paper we're about to do. Waves. Okay, waves is the waves unit, which is a vapor 2 unit. And then we get our electricity things, okay? So we've got charge flow equals current times time, potential difference equals current times resistance, power equals potential difference times current, power equals current times resistance, okay? And again, these two here. Now, I know I've probably rushed through them there, okay? But the key thing there, and the reason I've rushed through them, is remember that electricity is weird, okay? And scientists are idiotic when it comes to electricity, okay? Q, for some strange reason, is charge, okay? And it's measured in coulombs, which has the symbol C, okay? So even though, okay, charge starts with a C and it's measured in something which has the symbol C, its symbol is Q, okay? Yeah, Vincent Company leaving is going to be as much of a tragedy as your paper one, right? I, okay, is current, okay? That's really annoying, okay, because again, I in current. It's because the I actually makes it stand for induced current. You don't need to worry about that. But that is measured in amperes, which is A. Okay. Voltage is the nice easy one, which lures you into a false sense of security. So that is measured in volts. Okay, V. Now, one thing to note here is another word for voltage is potential difference. So whenever you see potential difference mentioned, that is also talking about voltage. And resistance, either. Okay, resistance is R equals is resistance. That's the symbol, and it is measured in ohms, which is that symbol. Okay, right. So in terms of what that means, okay, your equations that you've got in terms of this is Q equals IT, V equals IR. That one here is Ohm's law. Okay, we'll talk about that in a little bit because one of the things which people wanted me to go through was, oh God, there's so much hungry. Just calm yourself down. In terms of Ohm's law, okay, that's when we go through potential difference graphs. That's what it is. We'll talk about that. Equals potential difference times current. They're just different variations of it. Now, this P equals I squared R, if you're okay with algebra, you don't need to remember that one, because if you can remember P equals IV, and you know that V equals IR, if you say, well, P equals IV, V also equals IR, you can put them together, and that ends up with P equals I squared R. Okay, so if you know algebra and you know P equals IV and V equals IR, you can get that one. And that's it. Okay, that's probably overwhelmed you because you think, oh my God, we've got all those equations, but they're actually not too bad. You've got two ones which are repeated. You've got two energy ones, and then basically V equals IR is going to be your main electricity one. Okay, high T, you're probably going to be wanting to use PIV and PIR. That's a technical word there. Okay, if you need anything else particular with the equations, we can do that, but I'm going to call that ticked for now. Okay, in terms of pressure, pressure actually doesn't need much at combined. Okay, there's a little bit more in triple, which I think is why it's a little bit confusing. The only thing that you need in terms of pressure in combined is the pressure of gases, and you don't need to calculate it. You just need to know what pressure is. Okay, so if I have a container, okay, and I've filled that with a gas. Okay, while we're here, let's just complete the trifecta. Okay, so we've got solid, oh, so what did you do for revision last night? I watched Mr. Pashler draw random circles in boxes for an hour. Okay, so we've got solid over here. Okay, and that's where the particles are. They don't move. Okay, so they're kind of locked in place. They have high forces between the particles, and they also only vibrate. Okay, so you can think about that as the lowest energy or lowest kinetic energy of the particles. Okay, here, okay, you've got the particles no longer locked in place. This is a liquid, so this is where the particles can move over each other. It's kind of like a weird limp handshake, you know, when you have like kind of just random, like kind of, yeah, you know, when it's a crap handshake. That's where it all kind of goes over each other, okay, and that is the particles can move. You have, I'm going to say medium forces. Doesn't really matter. Is it's lower forces than a solid. Okay, and the particle and have kind of medium kinetic energy. Okay, because the particles are moving, so they're starting to move over one another. Okay, and over here you have a gas. Okay, and what happens is the particles bounce off one another, okay, and they bounce off all over the place, so they have random movement. They have random movement. They also have no forces. Okay. Oh, I appreciate that. That's a big compliment there, Ryan. You're such a suck up. So low to no forces. No, they have the highest kinetic energy. Okay, because they're moving all over the place. Now, this is where it comes back to pressure. The only thing in Trilogy, so combined science, that you need is to know that pressure is, because these particles are bouncing all over the stuff, they're going to hit into the walls. Okay, so pressure is when it bounces into the walls. Okay, cool. So, you know, the way that you have a pressure is where the particles bounce off the walls and exert a force on the walls of the container. That's it. Okay. You could say, therefore, that if I restrict the box, if I compress it, and I move the particles into a smaller space, they're going to bounce off the walls more, and that would increase the pressure. Okay. I don't think it will ask you the equation, but if it does, pressure equals force divided by area. That is not on the list, you'll notice. So they might give that. They'll give that to you. If they want you to do that, they'll give it to you. Okay. That is pressure and also the particle model there. So that's that one. Radiation. Okay. I'm actually going to combine that with atom models. So we're going to do atom models and then we'll do radiation. Okay. So. Bit ASMR. Huge. Right. Now, If I look at models, we start off at Dalton. Okay, and this is really big crossover with chemistry. Okay, right. I asked Nathaniel and Connor to be mods because last time it got a little bit inappropriate. All right, we don't need to start baiting them. Okay, I'll back them up. Okay, just calm yourself down. We're here at the end of the day. I just want to do some last minute physics with you. All right, there's something better. I can do better stuff with my evening. I could, you know. I started Assassin's Creed Rogue the other day. Got a bit of that. Right, so Dalton, he says that atoms are like solid balls. And this is exactly the same as the chemistry unit. Okay. Now, what happens is J.J. Thomson comes along and he discovers the electron. Okay, and the other day I said this, and what I said the other day was, if you'd never seen an Easter egg before, you'd assume that an Easter egg is solid. But if you actually interacted with an Easter egg, you'll finally discover that it's hollow. Okay, or if you've got an Easter egg, you'll discover little smarties inside. So J.J. Thomson discovers the electron. So what that means is it can't be solid balls anymore because he's discovered little parts which come from within. Okay, so what he does is he calls his model the plum pudding model. Okay, now this giant plus sign here is not like a feature of the atom. That's just saying the whole thing is positive. And then inside here are dotted negative electrons. Okay, so it calls this model the plum pudding model because it looks like a plum pudding. Okay, now we don't really get plum puddings much nowadays. You know, hot cross buns, fruit cake, anything like that. I also like to think of it as dessert spotted dick. Okay, because it's a way to remember it, from solid balls to spotted dick. I don't know, might remember that. Predictions for this paper? No idea, I'm not a wizard. If you know your stuff, it doesn't matter what comes up, that's the point. And also, if you don't know everything, it doesn't matter because you can kind of roll with the punches. A lot of the physics paper relies on your ability to take information and do something with it. Doesn't necessarily mean you need to remember it all. So when you think about equations, doesn't necessarily mean that you'll need to remember them all. But if you know how to work an equation, then you know how to answer really well. Okay, so we've got there. Next one we're going to do, and I don't know what colour scheme, too much purple, let's jazz it up. Okay, is what happens is we take Geiger and Marsden, and what they do is, and who are working on behalf of Ernest Rutherford, they take an alpha radiation source. Okay, and I can say that now because we're going to look at the types of radiation. And what they do is they take a very thin piece of gold foil. Okay, the only reason they take gold foil is because they can make it really thin. So the idea is essentially, you can think of this as atom thick. So if I zoomed in like this, okay, it's like one atom thick. Now remember, at this point, he assumes that the atoms are plum pudding model atoms. Okay, so if I took plum pudding model atoms, okay, where I've got the positive charge and these negative electrons like this, and I'm going to take an alpha particle. Now, alpha particles are 2 protons, 2 neutrons. Okay, what happens is they fire them at the thing. Now, if this is a plum pudding model atom, there's nothing in the way to kind of stop it. It just goes all the way through. No matter where the radiation comes, it goes all the way through. Okay. Now, the point is this: is that's not actually what they find. They find most of the time that the radiation goes all the way through. Then what they do is so they have a detector over here. Okay. Now they put it behind the gold foil, and then what they do is they kind of rotate it round, and just for gigs, they put it over here. Okay, and they want to see, does any radiation kind of come back? Because that'd be really weird. Okay. And what happens is they find that the radiation comes in and very rarely will get scattered all the way back. Okay. Now, if you were doing, I don't know, if you were firing like pellets at a piece of paper, okay, and all the like pellets go through, and then hit this point they bounce off, you'd assume that there's something kind of behind the paper, or something really like tough behind it, okay, and that's what kind of Rutherford assumes. He says that, well, actually, if I put all of the mass of the atom in this very tiny part, okay, that can account for it to come in and bounce back off, okay, and what he does is he calls this the nuclear model. Okay, he says that at the center of the atom there is a region of where all the mass is, and it's got all the positive charge. And what happens is the radiation comes in and bounces off. Okay, so Rutherford's model he says that we have a positive nucleus where we have electrons kind of doing that. Okay, this is your kind of Big Bang Theory kind of style. I hate that show almost as much as I hate koalas. Then that's that kind of model of the atom. Next thing is Bohr. Okay, who I said last time is boring because he is. He's Danish. That's got nothing to do with it. That sounds like I'm racist against Denmark. No, he's a physicist. He wins a Nobel Prize. So does his son. I'll have my rant about koalas another time. They're idiots. 90% of them have chlamydia. True. So what Bohr does is he says, or about 80%, something like that. He says that we have these energy levels, or shells. Okay. This is because he's a maths man, right? He basically, it's exactly the same as Rutherford's model, but he says that we have that. Okay, and we have these levels. Okay, that's Bohr. Now the other person, and last year people got really annoyed at it, was Chadwick. And what Chadwick does is, in 1935, he discovers the neutron, and that basically plumps up the nucleus. So it's exactly the same as that, but I'm not having a neutron in the middle. And that here is the model of the atom which we need to be familiar with. We've got electrons, protons in the middle, and neutrons, and they're in the nucleus. Okay, and we can talk about the charge. We can talk about the mass. Okay, so protons have +1 charge, and they have a mass of 1. Neutrons have no charge and a mass of 1. And electrons have a -1 charge and a mass of very small. Okay, that is the models of the atom. Okay, let's talk about this in terms of getting to radiation. Okay, now this is all the same as chemistry. The bit which makes it physics, okay, is take that nucleus. Okay, right. So when you look at the nucleus, you've got the protons and the neutrons. Okay. Now, let's go lime green. Let's mix it up. Lovely days. Okay. Protons are positive. There they are. Okay. If I take hydrogen, okay, and I look at the nucleus, okay, hydrogen 1, which is the most common isotope, has 1 proton. Okay. Just quickly, actually, if we're going to talk about isotopes, remember that there are 2 numbers associated with an atom. There is the atomic number, that's the number of protons, and then there's the mass number, and that is the number of protons and neutrons. Okay. If you look on the periodic table, okay, first of all, there is a key on the periodic table that tells you which one's which. But if you look at something like that, argon, okay, we've got 40 Ar18. This one up here is the mass number. This one up here is the atomic number. So if you had to say the number of protons, that would be 18, because that's the atomic number, and the atomic number is the number of protons, which is 18. Okay. Neutrons we'll come back to. Electrons in an atom, okay, it's the same as the number of protons, that's also 18. And the neutrons is going to be, well, if the mass number is number of protons and neutrons, and the atomic number is the number of protons, then 40 minus 18 will give you 22. I was saying about physics, it's really easy to get kind of in a wrong way with like the electricity stuff. We'll talk about that in a bit anyway. Okay. Yeah, so that's it. Now, what an isotope is, okay, is it's got the same number of protons, because the thing which actually defines the element is the atomic number, the number of protons, but it has different numbers of neutrons. Okay, so if I've got different numbers of neutrons, okay, it weighs different. So it's got the same atomic number, but it weighs different. Okay, and that's what an isotope is. Okay, it's like identical twins where one eats loads of food and the other one does loads of exercise. Okay, they look the same, but one's just a little bit chunkier. So hydrogen 1, okay, well, it has 1 proton. If I take something like, you also have hydrogen 2, okay, well, the atomic number of hydrogen is 1, so it has 1 proton. But that also means it now has 1 neutron. So you can see here that these are atoms of the same element because they've got the same number of protons, but this one's got an extra neutron. So they weigh different, and that's why you have isotopes. Okay. Now I can scale this up and start looking at more complicated things. Okay. So if I look at something, yeah, my internet's rubbish. It's probably that. Is it being really dodgy? Anyway, okay, cool. Yeah, it's probably because I'm not doing anything. I'll just move it back a little bit just to confuse it. It shouldn't matter. Yeah, so when I'm looking at that nucleus, we've got, if I take something like uranium, right, which has an atomic number of 92, you're suddenly putting 92 protons all packed together, right, 92 positives. And if you remember, the same charges repel. So you've got something, you've got 92 of these positive charges who really hate each other and they want to fly away. Okay, it's like putting 92 really like kind of angry boys in a room. They'll probably, what happens is they become what's called unstable, right? Where the nucleus will start to get so big and with so many like kind of light charges all shoved in there, they don't like it anymore. Okay, so what happens is the nucleus wants to decay. Okay, so we have unstable nuclei, and they want to kind of be stable again. So how do they do that? They've got 3 possible ways. Okay, alpha, beta, and gamma. Okay, so when I go back to, they're already dead. When you go back to the nucleus getting really big, okay, the easiest way to kind of start to make it small again is if a chunk of it flies off. Now, it just so happens that the way which it flies off is if I have 2 protons and 2 neutrons together in a lump, okay, and that's an alpha particle, okay. So it's made of 2 protons and 2 neutrons. Okay, also referred to as a helium nucleus, because if you take the electrons around the outside of helium, get rid of them, that's what you've got left. Okay, now this is a big brute, right? It has a mass of 4 because we've talked about all of that stuff, and it has an atomic number of 2. It's a big lumbering lump. Okay, so what that means is think of if you're playing rugby against a really like large bloke, right? And like a prop or something, if you know rugby positions, right? And if they hit you, it really hurts because they're really big, right? So they have a very high ionizing power. Okay. Now, what ionizing means is the ability. So if it hits an atom, it knocks off electrons. So this got a really high ionizing power because it's so big. If it hits an atom, it will knock off electrons quite nicely. But it also has a low penetration power. Okay, i.e., it's really easy to stop. Right. So again, go back to that really like large guy playing rugby. If he hits you, it really hurts, but he also gets out of breath really easily. Okay, he kind of uses up all of his energy really quickly. So alpha is really easily stopped by something like paper, your skin, oh dear, or a kind of few centimeters of air. Okay. Beta is, if I take something. Beta's weird. It usually happens like kind of lower down. Now, beta's kind of, again, as I said, weird. The kind of explanation for it can get to explain it. But the kind of the take-home message is you can think of beta as a fast-moving electron, and this stuff something isn't, and you still have kind of chemistry in the brain. You're thinking about electrons around the outside. So the weird thing about this is that it's an electron from the nucleus. Okay. Right. Is the stream okay? Is it working? I'll have a little ASMR coffee break just to check that it's all good. Chuck a bit of water in there as well. A bit healthy. Bit of healthy. That makes no sense. I can't like net radiation. I was working now. I'll take that. Cool. So it's a fast-moving electron from the nucleus. Okay. So let's just really quickly recap if it hasn't been working. Okay. Alpha is 2 protons, 2 neutrons, also known as a helium nucleus, and it comes. You've got a real fat nucleus, and it kind of breaks apart to kind of calm itself down. High ionizing power, because if someone who's really big runs into you, it hurts. Big people run out of breath really quickly. Okay, so they're easily stop skin or a ghost. No, paper, snow, a ghost. Paper, skin, or a few centimeters of air. Okay, beta, fast-moving electron from the nucleus. Okay, this has kind of got a medium of everything. Okay, it's got medium ionizing power because it's less of a chunky boy than the alpha nucleus. Okay. And it also has medium kind of penetration power. Okay, what that means, is it really bad? Is it really glitchy? I'm really sorry about that. Can you like hear me all okay? I know it's like, it's just me sat on my, and my internet. So yeah, apologies. You can't hear me. Audio's decent. Okay. Proper glitchy. Cool. Fun times. Let's see what I can do. I've got the very high-tech system of taking a clamp stand from school. Let's change the bit rate down. Let's say that I want to connect via USB. If this comes off, sorry. Let's make sure that I'm connected through USB. It's all right. No, I've heard that it's pretty glitchy anyway. Done. Okay. Right. Hopefully that might be a little bit better. Okay. It is plugged in, so it should be all right. Okay, let's hope that that's a little bit better. It's easy to stop by aluminium. Okay. Or aluminum for our American cousins. So if Mexican immigrants were electrons was beta radiation, Donald Trump would build his wall out of aluminium. Oh God, and that's awful. That's shocking. Cool. If I look at gamma radiation, okay, so gamma radiation is if you have got an atom, a nucleus which has got a little bit too much energy, and it releases that excess energy as a wave. Okay, so this is an electromagnetic wave. Okay, this is combined science, and this is in both stuff. Okay, there's a lot of crossover. There's not much higher only. It will just be a little bit more difficult equation stuff. Okay, now this has got a very low ionizing power because it's just a wave. Okay, very low ionizing power, but it's got like stupendously large high penetration power. Okay, what that means is it is really difficult to stop. Okay, my handwriting's gone. It's like you're an hour into. I'm kind of doing higher as I go as well, to be honest with you. It's like you're an hour into your English exam. And you look back and your first page is beautiful, and then you realise that your last page is barely legible. Okay, so it's really difficult to stop. The only thing which can kind of stop it is lead. Okay, lead is spelled like that. I don't know why I did that. It's because it theoretically can go through lead. The only thing is you can reduce it down so it's so indistinguishable from the background radiation that it doesn't matter. So what we can do with this stuff is okay. Now, if I take something like uranium, which has an atomic number of 92, and if I take uranium 238, okay, so that's the isotope of uranium 238. That means it has a mass number of 238, and it actually undergoes alpha decay, okay, because it's a chunky boy. Now, what happens is a bit of it breaks off, okay, and an alpha particle, if I look over here, okay, has got it's 2 protons and 2 neutrons, right? So that means that it's got a mass number of 4 and an atomic number of 2, because it's got 2 protons and it's got a mass number of 4. Okay. Now, the key thing with these equations is to make sure that the top equals the top and the bottom equals the bottom. Okay, so if I take this, right, I've got 238 breaks down into something plus 4, so that means the top is going to be 234. If I look at the bottom, I have 92, 2 of them have broken off, so it's going to be 90. Okay, so 90 plus 2 equals 92, and 234 plus 4 equals 238. So top equals top, bottom equals bottom. Now, the thing is this has actually changed the element because it's got a different number of protons. So if I actually look this up on the periodic table, it's the element thorium because it's got a 90 protons. So that's actually changed the element. Okay, so this is the decay equation for alpha radiation because I've got a chunk here which has come off. Okay, an alpha particle, and that's the same every time. If I take beta decay, a good example of something which undergoes beta decay is carbon-14. You don't need to remember these. I'm just doing them for the equation. Okay, now carbon-14, because isotope 14 has a mass number of 14. Carbon is C, and it has 6 protons. Okay, and this undergoes beta decay. Okay, now a beta particle has this symbol. Okay, it's got a mass number of 0 and an atomic number of -1. Okay, now it's a bit confusing. Okay, it's actually all to do with how that beta particle is formed. Okay, because I've got 6 here. Remember, top equals top, bottom equals bottom. 6 goes to something -1, so that's going to be 7. Okay, because 7 minus 1 is 6. Okay, and at the top, because that's 0, that's also going to be 14. So 14 plus 0 equals 14. Okay, and that means that that element is named nitrogen. Okay, has this really gone weird? Because I'm going really laggy again. Yeah, again, I'm sorry for my internet being rubbish. Your teacher's got paid enough, maybe I can get some fibre or something. Cool. Now gamma, you won't need to do the equation for, because gamma is just a wave. It's excess energy. Okay. And so, for instance, if I took, I don't know, uranium 235, uranium 92. I don't know if this does gamma decay. Okay. Is it that bad? Okay. It's actually not too bad, my end. But bear in mind that that when I'm done, it should all upload and watch back, and then you get like non-lagginess. So you've got 235 uranium 92. I don't know if this does gamma decay. I don't think it does, but YOLO. It's actually unaffected. You just kind of have excess energy because gamma is not a particle, it's just energy. So you don't need to worry about that. But the key thing here with all of these decay equations is that top equals top, bottom equals bottom. Okay. Oh god. Problem is I can't really restart the stream without kicking everyone off. If it continues to be that bad for some people, I'll restart it. But as I said, it might be worth a thing where I go through it, and then when I go, you can like kind of watch it back and think about the good. If I have a hard time reading the numbers, that's probably because my fours are weird, aren't they? Okay. Okay, so 238, 234 plus 4. Okay, the point is the top all equals together and the bottom all equals. That is radiation. The only things that I can ask you about that, really, and that's quite a good thing just to quickly cover before I go back to my list. If I look at a radiation graph, like kind of a decay, over time it kind of will go down. And the point is radioactive decay is completely random. It's a random process. Okay, like you don't know what the winning lottery numbers at the weekend will be, but you can probably predict the idea that someone will win the lottery this weekend. Okay, so it's the same thing for radiation. You don't know which radioactive nucleus is going to decay, but you know that overall, half of them will decay in a certain time. Okay, and that's what half-life is. So half-life, okay, is the time it takes for the radioactivity to halve. Okay, there's technically two definitions. Okay, you've got either the activity of the sample, which is what I've kind of done here, or also the number of atoms. If the number of atoms is half, it's the same thing. Okay, so if you have a look, okay, the time it takes to halve will be there. Okay, and if I have a look at that gap, okay, that's the half-life. Now you can confirm this because it doesn't matter where you start, the time it takes to halve is the half-life. So that's the time it takes to halve. If I look at a quarter, okay, which is half of a half, that distance there is the same as that distance there, roughly. I've just really sketched it, so don't worry about that, okay? But you've got a, the idea is it's constant, okay? So, for instance, carbon-14 has a half-life of 5,700 years. You don't need to remember that. But what that means is every 5,700 years I wait, the radiation of carbon will halve, right? So after 5,007 years, the radioactive level is going to be half. If I wait another 5,700 years, well, it's going to half a half, so it's going to be now a quarter left. If I wait another 5,700 years, it's going to maybe be an eighth, and so on, forth. Okay. Ryan, I've done radioactivity. I went through the equations and I've done models of the atom. So I've basically done, this was what I had at the start before I started, and I wanted to make sure I go through. So we've now done radiation and atom models. Okay, series and parallel and potential difference graph. So this is basically electricity. Let's build up electricity. Okay, right. So first of all, electricity is really, really weird to get your head around. Okay, I think I only first kind of got my head around electricity, like in a way where I actually understood what it was, almost when I started teaching it or at uni. So I could do all the equations, I could do all the stuff to do with it, but I didn't actually really appreciate what electricity was. Okay, so there are three kind of main components to electricity. The first thing is current. The second thing is potential difference or voltage. And the third thing is resistance. Okay. Now, okay, current is the flow of charge. Okay, or the rate of flow of charge, and that usually is electrons. Okay, so if I have a wire, right, you've got electrons moving through that wire. Okay, because if we remember, a metal structure is it's got delocalized electrons. So if I sat here with my super powerful pretend microscope, okay, and I counted how many electrons go past in a second, that's a measure of the current, right? A good analogy of this is if you wanted to look at the current of a river. It was geography today, so I hope I didn't give you too many flashbacks. If you're stood in a river and you look at how much water is flowing past you each second, that's the current or flow of the river, isn't it? Okay. For electricity, it's exactly the same thing, except instead of measuring how much water is going past you, you're measuring how much how many electrons, how much charge is going past each second. Okay, so that's what the current is. Voltage is kind of the ability of those electrons to do work, right? So what I like to think about that is kind of the push on the electrons, i.e., how much energy, how much pent upness have they got, right? So I'm measuring how many electrons are going past each second. If they're really charging through, okay, or if I look at them, if I look at those electrons, they look really muscly, really angry. That's a really high voltage. Okay, if they look a little bit weedy, okay, that's going to be a low voltage. So voltage is kind of how much energy, how much oomph does each of those electrons have. So we've got current, which is the flow. We've got voltage, which is kind of the how much oomph have they got. And resistance is anything which slows down the current, slows the flow. So it's a wire. The wire's made of atoms. They don't like electrons barging past, and they're annoying to get through. Okay, are in like a shopping centre or something, and everyone's milling about, and you're trying to make a beeline to a shop. Okay, you have to weave your way around people, and that's really annoying. Okay, so it's the same thing here. The electrons are trying to whiz around the atom. Now, there's a couple of ways you can start to think about resistance. If you've ever, I encourage you after the stream to look at Gladiators. Okay, Gladiators is an old 90s TV show. Okay, and what they did is there was different events that you would compete against, and one of them was called the Gauntlet. Okay, now what the Gauntlet does is you've got this kind of pipe like this. Okay, oh dear. You have this kind of semicircle kind of track like that. Okay, that you have to you start at one end. Okay, and you have to get to the end. Right, and in your way are okay. And what happens is you as a person have got to try and run through. Okay, and you know there's a lot of shoving all that time. So you are the current because you are the flow of electrons. Okay, because you are trying to get through. Okay, and so the rate at which people are going through that gauntlet is the current. The meters are your resistance. Okay, so they're trying to stop you. Another example would be roads on a motorway. Okay, you'll think of cars trying to flow through a motorway. Okay, like that. Anyway, let's not obscure because that'd be messy. Oh well. So you've got resistance. Now, if I think about how I can change this gauntlet, how I can change resistance, that'll explain resistance for you. Okay, so if I made this like kind of pipe that I have to run through, if I made that wider, okay, so it's now twice as wide, that will make it easier because you've got more space to run around the people. Okay, so if you've got more space to run around the people, that means that the resistance goes down. So as the width of the wire increases, okay, the resistance decreases, okay, because you've got more space to run around. If I made this longer, so I made it twice as long, so I made the length of the wire bigger, okay, that means I've got more through, okay, and if I've got more people to run through, that's going to be more difficult, and that means the resistance goes up, okay. If I went round and I told all of the gladiators that you are really ugly, okay, they're going to be really seething and angry, so that's going to be hot. It's going to be the temperature is increased, okay. And if they're really angry, that means that the resistance will increase, okay. How would a variable resistor do in this analogy? Okay, it's kind of like you can change how many people are in that tube. So you can choose if there's one person, you can choose if there's 4 people. Okay, cool. So that's how resistance affects the wire. Actually, while I'm here, I'm taking all manner of detours and kind of covering as much of the topic as possible. One of the required practicals for this topic is the resistance in a which is where you probably have had this, where you have kind of a ruler like this and a kind of a wire attached to the ruler. And what you did is you took your power pack, okay. You got your wire and you attached it there, okay. This went to an ammeter, attached another point, okay, and then attached to those wires there, you put the voltmeter, okay. Now, what happens is you then adjusted where it was, okay. And then you looked at V equals IR, okay, and that can calculate resistance, okay. So you had this length of wire with these crocodile clips. What you did is you moved it to separate locations, and you can look at how the length of wire affects resistance. And as we've just explained over here, the longer the wire, the longer the resistance. If I double the length of wire, it should double the resistance, okay. And also you could, another thing, variation of this they could do is they can, instead of changing the length of wire, you could do this experiment once with one wire and then use a different thickness of wire. And then you can look at how the thickness changes, okay, the resistance. So in terms of practical stuff, what they could ask, okay, is probably going to be a circuit diagram, okay, and I'll talk about where ammeters and voltmeters go in a second. Cool. So we've built up. We've introduced our 3 main things: current, voltage, resistance. Okay, and now what we need to do is look at how they what happens with them. Okay. So first of all, current, okay, is measured in amps, and it's measured using an ammeter. Okay, and this has the symbol A. Potential difference, or voltage, okay, is measured in, fun enough, volts, and this is using a voltmeter. Okay, okay. Now, before we think about how we connect them in, we need to know what series and parallel are. Okay. Okay. So series circuits. Oh, look at that time ahead. Right. Series circuits are ones where all the components come one after the other. Okay. So if I take 2 light bulbs, okay, so that's the symbol of a light bulb. That's a cell. Okay. If I have 3 light bulbs in series, they come one after the other and wear it around. I like to think with this about Netflix. No one just watches one episode on Netflix anymore. They watch one after the other after the other. Okay, a series, i.e., okay, it's basically a series. So series circuit, think of Netflix. You go one episode, then next episode, then the next episode, and you just keep going, right? All in one loop. Parallel, okay, Hopefully you know what parallel lines are from maths. Okay, they have their own loops. Okay, so series is all in one loop, and parallel, they have their own loops. Okay, so here I've got that. Now let's think about what happens here, right? Now let's go back to that river analogy. Okay, we said about current. Okay, so let's think about, we said that the rate of flow of things going past you is the current. How much oomph they've got is the voltage, right? And if I take a series circuit, it's all in one loop. So no matter where I look on this loop, the same amount of water is going to be flowing past, right? Because it's just one loop, okay? So that means that the current, all dark pink. I tell you what, see that, right? I've got these massive colouring pens, right? Some of these are just disgusting, right? Like, nobody ever uses the brown or the grey. I tell you what, let's be proactive. Let's use the grey, okay? Because it's such a horrible, boring colour, right? Current is the same, okay? No matter where I am on that loop, okay, because it's like one loop, the electrons flowing past at any point is the same. So the current is the same. Now, the amount of energy they've got, the voltage, okay? So if I look at the voltage, here, it's going to get to that light bulb, it's going to dump off some of its energy to make the light bulb shine. Then it's going to get to the next light bulb, dump off a bit more energy to make that shine. Get to that one, dump off a bit more energy, okay? So the voltage is actually shared, okay? So in a series circuit, okay, the current is the same and the voltage is shared. If I look at a parallel circuit then, let's go back to thinking about that river. Here, okay, I've got a flow of water, and then suddenly it's got a choice of two directions to take, okay? Does it go that way? Does it go that way? Now what that means is that the current is shared because the flow of electrons has now been like divvied up, okay? Because some of it will go this way and some of it will go that way. If I take the voltage, that's kind of how much effort it can give it. Because this one here knows it's got 3 light bulbs to light up. It's going to give some energy here, some energy here, some energy here. Whereas here, okay, it's going to give its energy here, and it can give it. It knows it's only got 1 light bulb. It's going to give it all it's got. Okay. So the voltage is now the same. So it's the opposite. Okay. So in a series circuit, the current is the same, the voltage is shared. In the parallel circuit, the current is shared and the voltage is the same. Okay. Generators. Generators is an electromagnetic device, so it's the other one. Okay, so that is your series and parallel circuits. Okay, current the same, voltage shared in a series, and a current shared voltage the same in the parallel. Okay. Now, here's the key. Going back to this. Okay. Is an ammeter, you want to measure the flow. You want to measure how much stuff is going through, okay, at any one point. Okay, so if you wanted to measure the flow of a river, you have to get in that river. You have to see how much water is flowing past you at any one point. So the ammeter always goes in series. Okay, that means it gets in the existing loop. Okay, now the voltmeter, right, is potential difference. It actually likes to compare the energy before and after. Right? So what it does is it kind of takes its own step back, relaxes, chillaxes, has its own loop, and they go in parallel. Okay, so whenever you're connecting up an ammeter, it always goes in series. Whenever you're connecting up a voltmeter, it always goes in parallel. Okay, so let's look at that. Okay. So if I took a battery again, and I have a component, let's have a resistor, like that. Okay, if I want to measure, okay, the current and the potential difference. Remember, okay, the ammeter is in series, and the voltmeter is in parallel. Okay, so what that means is if I want to put my ammeter in, it has to go in the existing circuit because ammeter's in series. So I'm going to put it there because it's in the existing circuit. Okay. Next, I want to look at the voltmeter. That goes in parallel. So what I'm going to do is I'm going to put it, make its own loop around the thing I want to measure. Okay, the voltage for. Okay. So the ammeter goes in series and the voltmeter goes in parallel. So this is very much, okay, like this quite a lot. They'll give you a circuit and they'll say place an ammeter and a voltmeter into the circuit in order to measure the current and resistance. Just remember that the ammeter goes in the existing loop and the voltmeter gets its own loop. Okay. Right. Now, that's series and parallel. Okay. Which then leads us on to, I know these are right at the start where I asked for topics, and some of you have probably been hanging on for an hour going, can we just go through it? National Grid and Transformers. Let me have a yes, you need to, I don't know if you need to, how much you need to know about the National Grid. Yeah, I don't, I'm not as completely encyclopedic on the specification for physics because obviously I know it all and I can do it all. But because I primarily teach mostly chemistry, I could just say go and rattle off the whole of the chemistry syllabus. But for the physics syllabus, I'm never completely sure what's in. Yeah, National Grid's in there. Okay, so the only thing which it says for National Grid is you need to know it's a system of cables and transformers linking power stations to consumers. Electrical power is transferred from power stations to consumers using National Grid. Step-up transformers are used to increase the potential difference, okay, and then step-down transformers decrease it to a much lower value. Students should be able to explain why the National Grid system is an efficient way to transfer energy, okay? So, so it's an efficient way to transfer energy because if I go back to this, right, if I'm trying to flow, they're going to get really hot and they're going to be really sweaty, okay? So if I take a wire, right, if I flow electrons through it, what happens is the electrons bump into the atoms and the wire gets hot, okay? And that radiates the energy, okay? So the logic is I don't want to lose energy because I've gone through all this effort to generate electricity. So what they do is instead of having a high current, what they do is you want as low a current as possible. So the electrons are just trickling through, but each electron has got loads of energy. So you want a really low current, but a super high potential difference. Okay. So again, you want low current because if the current, okay, is going to make the wire warm and it's going to lose energy. So what happens is you generate your electricity station, step up transformer. And what that does is that makes it into this low current, high potential difference. You go across your pylons like that. And then I go to a step down transformer and into your home. Okay. So the key thing here is the way it reduces energy loss and why it's efficient is because it has a low current, and this means that you have lower amounts of energy loss from thermal. Okay, because basically the wire doesn't get as hot. Okay. The other thing you need to know in terms of domestic supply, actually, while we're here, okay, I know I keep getting sidetracked, but I think it's good sidetracking. If I look at you need to know, okay. Okay, there are certain things that you need to know on the plug. Okay. First thing is this thing here, which is the cable grip. Okay, what that does is that, funny enough, grips the cable. So if you tug on a plug, you're not pulling all the wires out. It gives it a little bit of thing. Okay, now you have 3 pins to get to. Okay. The top one. Okay. Okay. The top one is an earth wire. Okay. Now that is exclusively for safety. Okay. So the earth is green and yellow. Okay. Now its potential difference is actually a 0 volts. Okay. And basically, what happens is all of the earth wires, when you plug them into the socket, all those top pins all link together and they go in the ground. Okay. That's why it's called the earth wire. So any problems is this is kind of like the safety wire. Any issues, the electricity will flow through this one and it will go into the ground and not through you. Okay. Okay. Now the blue wire here is the neutral wire. Now, if you're looking for a way to remember it, it's that BL. Okay, blue goes to the left. Okay, so the neutral wire goes to the left. BL, blue, neutral to the left. Now, this also actually has a potential difference on it of 0 volts. So if I looked at that wire and I put my thing there, it would actually show 0 volts coming out of that. That actually is that's actually at the substation. So all of the neutral wires kind of end up at the substation, decay, and that also has 0. Okay. The other one, and I'll tell you what, I moaned about brown, but here it comes. Okay, the brown wire. Now it doesn't go straight there. Mr. Pasha's made an error, right? What happens as we go here? Okay. Grey. Okay. So what's this? So this one here, okay, and I can use the same principle. BL, blue to the left here. BR, brown, goes to the right. Okay. Now the other way to remember this is a live wire is this is the one which carries electricity. Okay, it's 230 volts. Okay, way to remember this is if you get electrocuted, it's going to really hurt your teeth. 230 volts. Okay, so 230 volts because that's it hurts. Hurts your teeth. I don't know, your whole body, but it's going to hurt your teeth as well. The way to remember that this is the brown wire is because also it's the colour your trousers will go if you get electrocuted by it. Okay, so BR brown, which to the right is the live wire. This is the one which kind of gives the electricity, gives the power. Okay, it also goes through a fuse. Now, if I actually look in there, what it is basically a glass container, a very, very thin piece of wire. That is actually the circuit symbol for a fuse. Okay, so you usually rotate to the side. What happens is electricity goes through it, and that wire gets really hot. Okay, and if too much electricity flows through it, that wire gets so hot that it melts. Okay. Right, red is the old wiring standard. Okay, in the UK, it would not count. Okay, you need to remember these colours. This is the wire colours. Okay. So brown, live to the right, blue, neutral to the left. Okay, earth, green, yellow, Norwich to the top. Okay. Now the fuse. So as it gets really hot, what happens is that wire will melt and it will break the circuit. Because if you think about it, if I've now got rid of that component, the electricity can't flow and you've got nothing going on there. Okay. So that's your domestic supply. Okay, and with all the kind of bits of the plug. Cool. Right, finally we can get back to what I was going to do, which is those. No, it's not for triple science. It might be for your syllabus, but for AQA it is not. Okay? For AQA it is in the syllabus. Okay, I will copy a bit from the specification. If you're ever wondering if it's not in there, if it's in there or not, okay, you can always look at the specification. Okay. Oh no, 800 characters, doesn't like it. Okay. Yeah, basically, going rogue. What? That. Okay, you've got most electrical appliances are connected to that. Okay, live wire brown, ultra wire blue, earth wire green and yellow stripes. Okay. Okay. Cool. Potential difference graphs. Right. So remember when I said the required practical for a wire, we have this kind of ruler where we put a wire on it and we look at how its length and that changes. If I look at a resistor or that, okay, these things are actually, if I plot them on a graph, okay, remember these are what we call ohmic resistors. What this means is they obey Ohm's law. Okay, what is Ohm's law? It's V equals I times R. Okay, basically, the voltage, as the voltage increases, the current also increases. Okay, and resistance stays the same. Okay, so if I double the voltage, the current doubles. If I triple the voltage, the current triples. Okay. Now, this really only holds true if the temperature stays the same. Okay, if it gets hot, okay, it starts getting a little bit more aggy, and it means it's got more resistance. So if I was to plot this on a graph, okay, where put V there and I there, it would be a nice straight line like that. Whenever you see a nice straight line to do with potential difference graphs, okay, that means that that means that it's an ohmic resistor. When you see a straight line, that means it obeys Ohm's law. Okay, as the voltage increases, so does the current I. Okay, yeah, remember current is really weird. Current has a symbol I because scientists. Okay, so that is an ohmic resistor. Okay. Now, there's a couple of other variations. So these ones are non-ohmic devices. So we've got, let's combine them all. So we've got ohmic devices, which is basically a length of wire or a resistor, and you end up with that shape. Okay. You then have non-ohmic devices. Now, these are all ones where, for some reason, okay, or another, they disobey something to do with this, okay? Be it that the temperature changes or that there's some weird thing going on with the current, okay? So, the first would be something like a filament bulb. Okay, if you look at an old-fashioned light bulb, the way that they work is they have a very thin piece of wire in them, which gets really, really, really hot. Okay, it gets so hot it glows. Okay, and what that means is as the current gets up, basically less and less electricity can kind of flow. So you get this weird kind of S-shaped curve. Okay, and the reason that you get a curve rather than a straight line is because the wire gets hot. Okay. Okay. Next one, diode. Okay. Now, diode's really weird. A diode has the symbol it's like a play button, play pause button in a circle. Okay. Now what that means is electricity will flow in the direction of the arrow, but when it comes this way, it's kind of got a line blocking it, so the electricity doesn't go that way. So so diodes are like kind of one-way kind of valves. Yeah, they only let the electricity flow in one direction. Okay, so in the reverse direction here, no electricity flows. The line follows it like this. Then you have a very small lag phase, which just means it doesn't shoot up straight away. It just kind of continues a little bit, and then it goes up. Okay, so this is a diode. Basically, it only flows in one direction. Okay, cool. So that is a diode. Okay, so we've got so far an ohmic conductor, something like a wire or a resistor. Okay, if it's a straight line, that is a ohmic device. Non-ohmic, we've got a filament bulb, which is a curve because it gets hot. Diode only flows in one direction, and then okay, you've kind of got the opposite way around, which is a thermistor. Now, don't worry too much about this. Okay, I'm going to hazard a guess that a thermistor will not come up. Okay, because especially on foundation, the two ones they're really worried about are filament bulb and diode. Okay, let's again just check on the specification because I want to make sure I'm not teaching you wrong. Series of parallel circuits. Okay, don't worry about the graph. The only thing you need to know is that thermistor, okay, the resistance decreases with temperature, so it's weird. So as it gets hot, the temperature goes down, the resistance goes down. And the other one is a light-dependent resistor. And again, the more light, the resistance goes down. Okay, so that's all you need to know for them. They're very weird devices. Okay, I'm definitely seeing some sun still there, Mo. Not gonna lie, your iftar can wait. So, as the thermistor gets hot, the resistance goes down. The LDR, as you get more light, it goes down. Cool. So, ohmic, straight line. Non-ohmic, filament bulb like that. Diode, one direction. Thermistor resistance goes down. LDR resistance goes down. Whoop. Lovely job. I hate potential difference graphs. They are a pain. Right, Sankey diagrams is the only thing I have left from the original kind of list. I don't want to hang around for too long because it is 10 to 9. Sankey diagrams. Right. Sankey diagrams are a way of doing efficiency. Okay, so what efficiency is? Okay, is efficiency is your kind of useful output divided by your total times by 100. Okay, to make it a percentage. It doesn't actually need to necessarily be times by 100, but the 100 makes it a percentage. So a Sankey diagram is basically a visual way of doing this. Okay, don't worry too much about it. Okay, the key thing with a Sankey diagram is that you have is that whatever is useful continues on, and it's to scale. So if I take, say I've got a light bulb, right? A light bulb which takes in 100 joules of electrical energy, and it converts 20 joules of that into light energy. Okay. So what I'm going to do is I'm going to take the start. Now it's got 100 joules. So I could say, for instance, have a scale of like 1 centimeter being 100 joules, right? Okay, I'm pretty pleased with that for freehand. Okay, so the key of a Sankey diagram is that the useful continues. So the useful goes straight on, and the wasted kind of goes away. It's like go away, go away. Right. So this up here would be 20 joules. This up here is 100 joules. And this here, by process of elimination, well, if I start off with 100 joules, 20 of it went that way. That means that 80 joules went this way. Okay. Remember that whatever you have at the start, you have at the end. That is what we call conservation of energy. Okay. So that's a Sankey diagram. The key thing is that it has a scale, i.e. the fatter the arrow, the more energy. The useful energy continues on, and that waste energy goes away. If you're looking then at the useful bit, don't worry too much about Sankey diagrams. I'm not going to lie. I don't think they're going to ask you to do too much of them. The efficiency is going to be 200 divided by 20 divided by 100, because the useful output is 20. The total input was 100. So that's 20 divided by 100 times by 100, which is 20%. So that light bulb is 20% efficient. That's it with Sankey diagrams. Right, one more thing I will tell you is how to tackle any equation question. Okay. And those of you who have seen the wall in my classroom know and probably get annoyed at this. Okay. I will encourage you to use funky. Okay. It's funky, not fancy. Let's zoom out a little bit. Adjust the clamp stand. Lovely job. Okay. Don't tell the science department I've nicked the clamp stand. Yeah, don't tell me that I've nicked my own clamp stand. Cool. First thing to remember is you always write the formula down. Okay. Then you want to check the units. Then you want to put the numbers in. Then you calculate it. And then, because it was going to be func U for units again, but I got encouraged to not tell students to func U. It's you don't forget the units. Okay, so what does that mean? Right? If I had a question like, what is the kinetic kinetic energy of a 500 gram ball moving at 15 meters per second? Okay. So my equation is kinetic energy equals half times mass times velocity squared. Notice that's the first thing. Formula, I've written out the formula. Units check. You must make sure that you're always checking that the units are in what you call the standard units. So this is 500 grams. Now the standard units are actually kilograms. So what I'm going to do is I need to put that 500 grams into kilograms. Now that is actually 0.5 kilograms, half a kilogram. Okay. So that's our units check. Numbers in. What I'm going to do is I'm going to rewrite everything I've done here, but put in the numbers from the question. So my kinetic energy equals a half times mass, which is 0.5, times velocity, which is 15 from the question, squared. That's my numbers in. Great. So that means I actually do the maths. Okay. Waves is second. It's paper 2 for AQA. Half times 0.5 times 15 squared. So calculator. Okay. That would be a quarter times 225, which is 50.2. Okay. That's the calculate. Okay. You don't forget the units. At the end, kinetic energy is measured in joules, so I must write joules at the end. Okay. Cool. So that is how you answer any equation question. Make sure that you follow those steps. The reason being is that you would get a mark for various points in this. You would get a mark if they hadn't given you the question, you would get that. Okay. If you'd get a mark for the conversion, you'd get a mark in. If they did this freehand, you'd probably get 5 marks. And that's probably strong. It's probably going to be a 4-mark question if they don't give you the equation. Okay. Sometimes 3. But the point is it's usually a mark for the answer, and you get some marks for working out. At the very least, if you get that wrong, okay, if you get that wrong, the key thing here is to at least make sure that you're getting the working out, because then you can get marks up until that point. Right, that's everything that I've been asked to go through. I've probably got time for another couple of quick things if you want me to go through them. Okay, anything that you'd like me to go through? Or I've got a past paper and I can quickly do a couple of questions from that if you like. I'll have a cheeky crisp. No one got anything? Is that just you want me to start off? Past paper? Well, the practicals, that's a good point. Right. Okay. What flavour crisps? That is salt and vinegar. They're on offer. Beautiful job. Right. Right. Practical assessment. Salt, salt, don't need that one. Okay, required practicals for this one. So you've got specific heat capacity practical. You have got the circuit one with the length of wire, which we've already covered, slash width of wire as well. Check that's all okay. Oh dear. You also have the same thing, but you kind of, instead of clicking up those things, you use a bulb or diode. I'll quickly show you the circuit diagram for that. The density practical. Everyone loves the density practical. Lovely, that's it. Right. Okay. Specific latent heat, I believe, is actually only on triple. Oh, no, it's not. It isn't. It is on this. But you could give an equation of specific latent heat, so YOLO. YOLO doesn't make any sense in that situation. Shannon, you're not, but you're also in year 9, so you're perfectly prepared for GCSE. Right. So let's take these one by one. Cheers. Cool. Whoop. Right. The circuit. As I said, the circuit diagram. If I take a power pack or battery or something, okay. If I connect it up to the wire, okay. So if I have a length of wire here, okay, and I can change the distance, okay, here. So I can put wire. The ammeter goes in the loop, remember, because ammeter always goes in series. The voltmeter always goes in parallel. So here you can see it's got its own kind of loop around this. That's a circuit diagram. Now, that's for the length of wire slash width, because what you can do is you can change where you put it on the wire, or you can change the width of the wire. The other version, okay, is that instead of having that wire there, you replace it with something like a diode. Yeah, conventional current, that works. And then I can have voltmeter there, ammeter there, exactly the same. But instead of the wire, you've got a diode now, or you could put a filament bulb. Okay. Occasionally, they'll suggest that you put a variable resistor in there. Okay, and that's so you don't kind of overheat everything. Okay, that is your circuit ones. Okay, I don't think they're going to ask. They can, to be honest, if they ask you how do you set that up, just draw the circuit diagram. Like that's it. Okay, specific heat capacity. This is the one where you had a block of metal. Okay, so for instance, like this. Okay, and it usually had two holes cut in it. You had a big hole and then you had a little hole. Now in there you put a thermometer, and in here you put an immersion heater. Okay, and that immersion heater you then connected to the electricity. Okay, I'm going to do that because it's actually an alternating current. Don't worry about that. Okay, so how do you do this practical? What you do is you put the heater in, you put the thermometer in, you measure the temperature at the start. Okay, so say that is 20 degrees. Okay, you then turn on the heater. Okay, now the heater will have a power, so it might have 50 watts or something. And what that means is every second that that's on, it is using 50 joules of energy. So you then turn it on and you say time it for 10 minutes. Okay, so if you've got 10 minutes of 50 watts, okay, what that means is you're for 10 minutes, every second you're using 50 joules. Now, bear in mind, it's actually one of our equations is that V equals power times time. Well, the power is 50, okay? The time is 10 minutes, but that's when we've got to put that into seconds. So that'll be 600 seconds. And that will give you 3,300, 3,000, 30,000 joules. Yeah, I think so. Yeah, cool. So that means in the 10 minutes I have that heater on, it will have transferred 30,000 joules to the metal. I'm then going to measure the temperature at the end of those 10 minutes. So say it's gone up to 59, something like that. Let's do that. Okay. Now, this equation you do not need to remember. It will give you the equation. Okay. You will also never have to rearrange this equation. So it is specific heat capacity equals mass times. Sorry, hang on. It will give it to you. The specific heat capacity equals mass times energy. Specific heat capacity equals energy divided by mass times change in temperature. Okay, that is a rearranged version of energy equals mass times specific heat capacity times temperature. I strongly suspect that they will only give it to you in this format. Okay, and that is the only format that you need to know. Okay, Olivia, this is the specific heat capacity practical, where you had a big lump of metal and you put a heater in it and you measured how hot it got after like 5-10 minutes. Okay, so the method: get a block of metal, put in an immersion heater, put in a thermometer. Step 2, measure the temperature at the start. Step 3, turn on the heater and start a stopwatch. Step 4, okay, stop the stopwatch and turn off the heater, okay, and measure the end temperature. Then, using the temperature change and the power of the heater and the time it was on, you can calculate specific heat capacity. That's all you probably need to say if you ask a method. Okay, so we can use that and we can calculate it. So say I use 30,000 joules. It was that. You also need to actually, that's one thing I mistake. You need to weigh the metal. Okay, you need to weigh the metal because then you know how much you're heating up. Okay, so the mass, it's usually 1 kilogram. Okay, and then you can work it out. So the steps, okay, is 1, weigh metal, add heater and thermometer. Okay, 2, measure start temp. 3, turn on heater and start watch. 4, turn off heater and measure temperature. Okay. 5, you then using the temp change, use the time and the mass at the start, and then you can work out specific heat capacity. That's it. Okay, safety points. It gets hot. There you go. Don't burn yourself. Okay, cool. That's the specific heat capacity practical. The last practical and the last thing I'm going to do, because it's 9:10, unless anyone's got anything burning while I go through this that they want me to go through. If you say, just shout, I will go through something if you need me to. Is the density practical. Now, I'm going to go out on a limb here. I'm going to say this is probably what's going to come up in terms of the practical. It is measuring the density of an irregular solid. Okay. So this means it is not a nice lump. Okay. I don't think live streaming is for Mr. Russell. I don't think he's a live streamer. Cool. I don't think I'm a live streamer anyway, but I've been coerced into it. So if I take virtual, the way we calculate density is it is mass divided by volume. Okay, so we need some way to measure the mass. We need some way to measure the volume. Okay, and then we can calculate the density. So the mass is nice and simple. You put it on a scale. Okay. I've never played Apex Legends, nor do I intend to. Volume. Okay. Now volume is if it was a nice block, it'd be really easy because I'd measure the sides of it. So if it was a cube, I can measure it and do it like that. But notice how this is the density of an irregular solid. So that means it's not nice. So you have to use a couple of snazzy ways of doing this. Okay. No, I used to. I haven't for ages. Last one I got was Modern Warfare 3. What you do is there's 2 ways of doing this. You can either use something called an Archimedes flask, which is you take this thing like this. Okay, it's a beaker and it's got a spout here. Okay, and the water's filled up here. So can you see that any increase here, the water will rise up and go down here? Okay, the Eureka can, that's the one, right? Not an Archimedes can, Eureka can, that's the one. Okay, what happens, so then is what I'd take a measuring cylinder, I drop the irregular thing in here, so say it's like this, blah, blah, drop it in there, that will make the water level rise, the water will flow out of here, and I can measure the volume. So how much that displaces will tell you the volume. Okay, no, come on, I'm not telling you my PlayStation name. I mean, it's not hard to work out. Okay. So that's one way. The other way you can do it is you can take a measuring cylinder, okay, filled with water, and then you can drop the object in, okay, and then the level will rise, and then you can look at the change. So there's two ways of doing it. You either use a Eureka can and have a measuring cylinder there, and you can measure how much it goes, or you can have a measuring cylinder, put something in, the level rises, and then that tells you the change. So now you've got the volume, you can put it into there. So the method for this practical will be one, weigh the object. Now, the reason you always do that first is because if I put it in the water, it's going to get wet, and therefore you'll have water stick to it, it'll be heavier. So first of all, you weigh the object. Second, okay, you either place into a Eureka can or a measuring cylinder, with water, okay, and then you can use that to measure the volume, and then for density equals mass divided by volume. Okay, questions that they could ask about is remember to weigh it before, okay, before you do the volume. Right, that is all the required practicals. Anything else? Last call. I wasn't going to go. No, I'm not going to go to bed, but I don't know, because it's actually quite tiring. Yes, you can. I would strongly suggest if you are doing a method, draw a diagram, label diagram, get marks. Okay. Foundation, you'll tend to be given the equations. Okay, but otherwise you need to remember them. Okay, I went through them right at the start. Okay, again, this is AQA if you're not an AQA person, so I don't recognise your name as someone I teach. These ones here in purple are this paper. So kinetic energy equals times mass times speed squared. GPE equals that. Power is energy divided by time. Efficiency equals useful output divided by useful input. Charge equals current times time. Potential difference equals current times voltage. Power equals that, blah, 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 blah. Okay, anything else? Last call. It's not sarcasm I detect, is that, Olivia? I hope not. Thank you for sticking about. If you find this useful, again, I'll keep doing it. I think obviously it's less of a novelty this time. So I think actually there was a lot of stuff which it was a lot more. I think got a lot more content today. If you find it useful, I'll keep doing it. Yeah. Obviously, I teach the chemistry more. Okay, you need big help. I should be about before school if you want me to go through a couple of things with you. So I hope you find that all right. I don't mind doing it because I've just got my pajamas on, got some crisps, cup of tea, job done, and I'm just talking to myself. Yeah. Good luck, everyone.